Phase-locked loop, a review. Abstract phase-locked loop act as colossal role towards the expansion of the ASIC, application-specified integrated circuits. With this technology, the delay time of the circuits was decreased. It is primary building block for several devices, like clock pulse creation, microprocessors, fasten the circuits and lots of. The essential quality like locking capability of this locked loop, it can be present in various applications. At the present time, wireless equipments can show the way in our lives. All engineering mind focused on the teeniness of the circuits, mechanism and dimensions the devices. The RF communication is indispensable for promptness of data transition in wireless systems. Through the frequency synthesis, RF transmission use steady timing signals to be generated by phase-locked loop. After detailed study of many papers, the performance, design, and enlargement of PLL circuit is framed. Introduction. Phase-lock loop is a fundamental part of radio, wireless, and telecommunication technology. Nowadays digital systems are using clocks for sequencing their operations and synchronizing different functional units. The most versatile application of phase-locked loops, PLL, is clock generation and clock recovery. The data transfer rates and clock frequencies have been constantly increasing with every generation of processing technology. Because of the increase in the speed of the circuit operation, there is a need of a PLL circuit with faster locking ability. The history of the phase-locked loop dates back to as early as 1932. According to author Dr. Roland Best, the French engineer de Belle-Size is the inventor of coherent communication. Phase-locked loops, PLLs, are extensively used to generate well-timed on-chip clocks to be used in high-performance digital systems. Phase-locked loop is a closed-loop system which locks the phase of its output signal to reference input signal. PLL is a mixed signal circuit as its architecture involves both digital and analog signal processing units. Classification of PLLs. Using the notation of Best 8 and Gardner in 9, the different classes of PLLs are as follows. 1. Analog phase-locked loop, PLL. 2. Digital phase-locked loop, DPLL. 3. All-digital phase-locked loop, ADPL. On the basis of component used, the PLL can be divided into subsections, given in Table 1. 2. Related work. In 2019, Shruti Hathvalia and Naresh Grover 14, presented a comparative study on DPLL. In that research they present a relative review of ring oscillator and LC oscillator for PLL. They also discuss both the oscillator's parameters and pros and cons of the systems. Leijong et al. 15, uses a fast acquisition PFD to eliminate non-ideal effects of PLL. 65 nanometers technology is used for designing a PFD. This consumes the area of 0.0016 mm2 for 1.5 MW power only. By the simulation, the maximum operating frequency is 5 GHz. Ushakumari and Rekayadov 12 reviews an article on digital PLL. They had discussed about the basic building blocks and the features of them. By the comparison analysis they concluded a circuit having low noise and better control range. The circuit is basically used for receivers and wireless systems. Suprajitiram Lasetti et al. 16, proposed reduces jitter PFD to increase the lock range of PLL. It uses the pass transistor to increase the rise time. The operating frequency of this is 5 MHz with delay of 2.93 seconds. Leela Bitla et al. 17, presented a paper on analysis of NAND gate-based phase frequency detector for phase-locked loop. The PFD designed for this is a NAND gate-based that consume appreciably low power over different temperature variation. The range of slew rate is 44 V/ns, 30 V/ns on 65 degrees Celsius. Shankar Andandra and Ankita H. Deshmukh 6, designed DPLL using 45 nanometers technology. X or phase detector is used for DPLL. The VDD is 0.9 V with input frequency of 2.4 GHz. The lock frequency of DPLL is 7.1 GHz at 0.9 V control voltage. Loop is locked at 2.4 GHz frequency. In 2017, Nabiha Ahmed ETAL19 obtained a tri-state CP and second-order LPF used in PLL system. The projected design has been simulated by 130 nanometers technology in Cadence tool at 1.2 V supply. The throughput swing is 288 MV to 413.8 MV at 4.7 GHz frequency. The layout area measurement is 31.4 m x 22.6 m, 0.7096 mm2. Ganda Bhargav ETAL20 devised a PLL by adjusting the values of CP and LPF. The locking time is about 1.5 s at 1 V supply. The total power consumption of oscillator is 0.5 UW. CMOS technology, 90 nanometers, is used for the proposed design. 3 Region of operation of PLL. The PLL have 3 basic regions of operation for which it can work. If it is not locked, input and output are on different phase, PLL is in dynamic state. And if both phases are same, it is called as static state. Fig 1, PLL region of operation. A hold range. It is the range of frequencies in which PLL can maintain phase tracking between input and output. If reference frequency is gradually condensed or enlarged, the PLL will be unable to find lock. This is called hold range. It will be temporarily stable just in this range 9. B pull-in range. In dynamic state it will constantly locked. Initially PLL is unlocked. It will obtain lock state if reference frequency is applied in the pull-in range. If input frequency is outside then the PLL will never acquire lock condition. See lock range. The range frequencies from which loop can uphold the lock state. All the region of operation is shown in the Fig 1. D pull-out range. The frequency, facilitate the PLL to release. If input frequency is below the pull-out range the PLL remain lock. On the other hand if it will exceed, PLL will not be capable to follow the output signal. After some time it may obtain lock. It is called static state of PLL. For operation of PLL. The analog PLL is built with entirely analog functional blocks. The basic block diagram of an analog PLL is shown in Fig 2. A PLL is a closed-loop feedback system that sets fixed phase relationship between its phase of output clock and the phase of a reference clock 9. This is used to track the phase changes that are within the bandwidth of the PLL. PLL also multiplies a low-frequency reference clock .I, to produce a high-frequency clock or feedback clock .O. An analog multiplier is used as the phase detector, PD, to produces an error output signal based on the phase difference between the feedback clock and the reference clock 10, 11. The phase difference signal is applied to the loop filter. The loop filter is basically a low-pass filter, built with passive or active components. The filtered error signal acts as a control signal, voltage or current, to the oscillator and adjusts the frequency of oscillation to align feedback phase to the reference phase. The voltage-controlled oscillator, VCO, is a ring oscillator constructed by differential inverter stages. As a result, the VCO changes its operating frequency, hence changes the output feedback signal. This output signal is fed back to the phase detector. The phase detector detects the new phase difference again and the same feedback process occurs. In this way, the phase error vanishes eventually and the phase locking is completed. A 4-quadrant multiplier phase detector is shown in Fig. 312, which is an ideal analog design. The phase detector is a multiplier and it is applied for determining the phase relationship between the reference clock and the feedback clock. The output of the multiplier is made up of 2 periodic waveforms. One frequency is the difference of the 2 input sinusoids and the output wave's frequency is their sum 9. If we have 2 sinusoids S1 and S2, both have same frequency but have phase difference of 90 degree. By multiplying these 2 signals, S3 signal is obtained. We take S1 and S2 as sine and cosine signal respectively, where Km is the gain of the multiplier. By the above equation, the multiplier signal S3 consists of two parts. The first one is the function of only the phase difference of two signals, and the second term is the frequency, which is twice of the signal frequency plus the sum of the two phases. The second part of the equation is the high frequency component, and it can be discarded by filtering out since it does not contain any necessary information. V. Comparison of PLL parameters. The different comparison parameters of all the components are shown by tables I, 2 and 3. 1. XOR. It will generate the output voltage for both the cycles of input pulse. The data losses occurred, because that is not sensitive for both edges. 2. JK flip-flop. The data losses will not be occurred because that is sensitive for both clock edges. It produced larger phase tracking and the angle is minus 180 degrees to 180 degrees phase error. 3. PFD. The phase error shifted for minus 360 degrees to 360 degrees. It will lock the input for different conditions. Circuit complexity is high as the numbers of components are more than other phase detectors. S.No. Type. Advantages. Disadvantages. 1. Active filter. In this filter, load resistance does not affect the operation of circuit. At the high frequency, circuit output is not fixed. Bandwidth of the circuit can be easily adjusted by varying the parameters of the circuit. The throughput is unreliable at high frequencies. It provides good isolation between load and the circuit components. As the change in the input voltage occurs, it will openly change the output of the circuit. 2. Passive filter. Easy to design and compact, light in weight. Q factor is low. Works on very high frequency, so it will suffer with noise. It cannot reduce the ripples. Enhances the circuit complexity. It will easily alter the control voltage. No isolation required between load and the circuit. Modulate the clock frequency so the clock pulse will vary. Q factor is high. It becomes costly as active components are used. Table 3. Advantages and disadvantages of VCO. Voltage control oscillator. S.No. Type. Advantages. Disadvantages. 1. LC oscillator. Squad phase noise. Outsized layout area - larger area for inductor. Excellent stability. Tank networks may have resultant resonant frequencies, which cause unwanted performance loss to the circuit. Low jitter performance of the circuit. Constricted tuning range, require lot of classification to tune, and it has supplementary complex design. 2. Ring. Simple to integrate. Reduced phase noise. Superior phase noise. Hardly ever worn for RF systems. Phase generation is 360 degrees at the time of oscillation, and it is used in elevated data links. It will suffer with jitter problems. 6. Result and conclusion. The purpose is to limit the center frequency by the scaling of transistor at the different levels. As a result, the locking time of the PLL is reduced as compared to the paper 14. As the same supply voltage is used in both papers, transistor's size would change the all parameters. The oscillation frequency is far better to the compared paper. The power consumption is almost 1.08 MW with 5 stages of oscillator. The comparison parameters are shown in following. Phase frequency detector is designed by the D flip-flop, so one glitch is coming at the simulation result at 1.06 ns time period. These pulses can change the control voltage for VCO. The maximum peak occurs at 98.76 MHz frequency.